commercial break. I said, as bodies go up, they decelerate, but this deceleration is due to gravity. That is why for vertically upward motions, A in linear equations changes to J, but this J is negative, okay, because it's a deceleration. And the equation for vertically upward motion becomes V is equal to U minus JT, because this is not an acceleration, it's a deceleration denoted by the negative sign. But who causes it? This deceleration is caused by gravity, hence A changes to G. All right. Now, if a body is falling downwards, this time the body accelerates. Because, hey, I'm not recording. Oh, recording in progress, sorry. The body accelerates. When a body is falling downwards, okay, its speed increases. Its speed increases. But the acceleration of the body, okay, is constant irrespective of the mass. Whether the body is small or the mass is large, the two bodies would accelerate by the same margin, 9.81 meter per second squared. So irrespective of the masses, we expect the two bodies to fall at the same time because they are all influenced by that magnitude of the force which pushes them down to the center of the earth. So when I drop a stone and a feather, I expect them to fall at the same time. I know this will call for a lot of questions, and I'm waiting for your questions. When you drop a stone and a feather, they are all expected to fall at the same time because they all would have the same force and they all have the same acceleration acting on them. So they are expected to fall to the ground at the same time. Your questions. I'll go see our first one.
Yeah, but what is the emotion?
Pardon?
What is the emotion? How is it going to fall the same?
Nice question. I'll answer. Another question. Another question. No question. Okay. Yeah, so falling objects accelerate by the same magnitude. And so no matter how small or big the mass, they are all expected to fall, okay, fall to the ground at the same time. But this is on condition that there is no external force acting on them other than gravity. And so it means that if we have wind blowing, when there is air resistance, it won't work. And on the surface of the earth, okay, or within our space environment, this doesn't work. When we drop a stone and a feather, the stone will certainly drop before the feather. Please, is that correct?
Yes.
Good. It's because there is air resistance around. The air resistance will surely affect the mass, the lighter mass. And so this rule that because the same value of acceleration acts on the same two different masses, they need to accelerate by the same rate, wouldn't work. It works on condition that air resistance and all other external factors are not there. And so the The first person, the first scientist to conduct this simple experiment was Galileo. Galileo, an Italian scientist or physicist, okay, stood on a tower and then dropped two different masses under the condition that there was virtually no air resistance, air blowing, and any other factors. And he saw that the two different masses dropped at the same time. At home, if you could have a situation where wind velocity is very, very low or not in existence, put off your fans and drop two different masses and you see it for yourself. Then an American scientist, astronaut by name Neil Armstrong, also performed the same experiment on the moon. He dropped a hammer. Okay, he dropped a hammer and a coin, and then saw that yes, the two bodies dropped to the ground at the same time. On the moon, gravity is very, very less, 1.64 meters per second squared. He dropped the hammer and the coin, and they all got to the floor at the same time. Please, this experiment conducted by Neil Armstrong is on YouTube. You can Google to look at it. Is that okay? So, when bodies are falling and the only force which acts on them is the force of gravity, then we say the bodies are falling freely or are in free fall. So we talk about free fall when the only force acting on a falling body is due to gravity in the absence of all other forces such as air resistance, drag is air resistance, and all other external factors. So for free falling, we expect only force of gravity to be acting on the body. Okay, and when bodies fall freely, they fall at a constant acceleration equal to 9.8 meters per second squared. So here, when you plot the velocity time graph for a free falling body, the velocity time graph for a free falling body velocity time graph. Let's bring the unit meter per second / second. For a free falling body. For a free falling body, it is a straight line. The slope certainly would give you that the constant acceleration due to gravity. Equal to 9.8 meters per second squared. Okay, now when bodies fall freely, okay, because there's no other force acting on them, the initial velocity of the body is 0. That is why Yaba, in solving the problem, represented V to be equal to 0. I questioned and she couldn't answer. Because when the body gets to the maximum height and is falling back, it is free falling. And when bodies are free falling, the initial velocity U is equal to 0. Please, are we okay?
Yes, please.
When bodies are free falling, the initial velocity U is equal to 0 because there is no other force acting on them. So look at this scenario. If somebody finds his or herself on top of a coconut tree and the person desires to fall, there is nothing much the person is expected to do. All that he or she needs to do is to get his or herself detached from whatever holds holds him, and gravity will do the rest for the person. Okay? If you are sitting on top of whatever and you want to fall, all that you have to do is to detach yourself, and gravity will bring you. So for free falling bodies, initial velocity is equal to 0. But what is the final velocity? You see, when bodies are falling freely, they accelerate. And every acceleration is characterized by what? Every acceleration is characterized by what?
Velocity.
Come again.
Velocity with time.
Come again.
9
Velocity with time.
Velocity with time. But you see,
With respect.
Okay, let me come in. Every acceleration is characterized by increasing velocity. And every deceleration is characterized by what?
Decreasing velocity.
Decreasing velocity. So if the body is falling freely and the initial velocity is equal to 0, as the body falls or as times go by, the velocity of the body at different times will be what? Increasing, isn't it? Isn't it? So after T1 seconds, the velocity here would have to be greater than the velocity at the beginning point. After T2 seconds, the velocity here, let's label them. This is V1, V2, V3. Because as the body falls, the body accelerates. It means that V1 must be greater than U, which is equal to 0, because the body is free falling. At time t is equal to 2, V2 must be greater than V1. At t is equal to 3, V3 must be greater than V2. Just before the body drops to the ground, it is falling with the maximum velocity. Just few seconds before the body hits the ground, it is falling with the maximum velocity, because when the body hits the ground, it has come to a stop. So the velocity is 0. That's why I'm saying that just before the body hits the ground, it is falling with the maximum velocity. Please ask your questions if you have any. No question? All right. So when a body is free falling, please put this information down. When a body is free falling, its velocity increases. That is why we say the body accelerates due to gravity. The body accelerates due to gravity. Okay, but at the starting point, the initial velocity is 0. As time increases, or at different times, the velocity also increases accordingly. And that is why the body is said to be accelerating due to gravity. Class, is that okay?
Mr. Ada, please, can you repeat the sentence?
Gloria, which sentence?
Please, the
What
one
you
you
watch
just said.
When you said when a body is free falling.
When the body is free falling.
Okay, when a body is free falling, okay, the body's velocity increases with time. The body's velocity increases with time. And it is for that reason that we say that the body accelerates. And it is for that reason that we say the body accelerates. Don't forget, acceleration is characterized by increasing velocity with time. And so, please write this too. We are considering as the body falls from, okay, this place, we are considering at the time T1, T2, T3, what is happening to the velocity. So T1 goes with velocity V1, V2, V3. But V1 is expected to be greater than the initial velocity, which is 0 because the body is free falling. Then V2 is expected to be greater than V1. V3 is also expected to be greater than V2. Akosia, your hand.
Yeah, please, she said with free falling, the acceleration is constant. And you also said that the velocity increases. So if the velocity is increasing, how come the acceleration is still the same?
Acceleration is constant or uniform. From Akosia, we've done uniform accelerated motion. And what happens in uniform accelerated motion? In uniform accelerated motion, the rate of change of velocity with respect to time is constant. And so if you plot a velocity time graph, it is inclined to the time axis at a constant angle. And so the acceleration along this is constant. Don't forget, I just gave you the velocity time graph for the acceleration of a body in free fall. Are you answered? Akosia, are you answered? Okay. So let's write equation for vertically downward motion. So for vertically downward motion, yes, V is equal to, class, will that be plus or minus? V would be equal to the first one. Okay, help me derive it.
V is equal to U plus GT.
Good. Why is it plus?
Because the body is
accelerating. Good. And the acceleration is due to
increasing velocity.
That is why it's due to gravity. That is why A has changed to G. Okay. Then the second one, S is equal to
UT plus
what? Half JT squared. Okay. And finally,
V squared is equal to U squared plus 2GS.
good. And because we are talking about vertical height, let's change all the S to H. Okay. Now, for free falling, because initial velocity is equal to 0, we have, these are the equations for free falling bodies. V is equal to JT. H is equal to half JT squared. V squared is equal to 2JH, and V is equal to square root of 2JH. for free falling, because the initial velocity is 0, these are the equations used for free falling bodies. Okay, now look at it. Look at two situations. If I have two different oranges, one in my left hand and right hand, and then I leave this one to fall freely, but the other one I give it a push. This is free falling because it will accelerate due to gravity. This is not free falling because it will accelerate due to the force applied. And when you have the two situations created, you let one fall freely and you give one a push. This one will drop before the one being left to fall freely, because the one that is left to fall freely would accelerate due to gravity, but this one, you are giving it a further push. So it's like another external force acting on it. So there will be acceleration, but not due to gravity. So look at the two different scenarios. There may be questions. I'll even give you questions to that effect. Okay, where two different objects, one is made to fall freely and one has a force acting on it. Anyway, when the question comes, we'll know what to do. So let's go back to look at our last question. Okay. With what velocity will it return to the ground? So when the body gets to the maximum height, one is projected from here and it gets to the maximum height, and it is falling. The moment it gets to the maximum height and gets ready to come down, because here the body is seen to be free falling at the maximum height, just upon the return of the body to its position of throw, at the maximum height, right at this position of the body is free falling. And so quickly the initial velocity becomes 0. But because it is free falling, at different times we expect the velocities to be increasing. Just before it hits the ground or strikes the ground, fine, the velocity is 0. So we are looking at just before it hits or falls to the ground. So using any of these, we can use V is equal to square root of 2JH. What is the H? H is the maximum height we calculated. And what did we get for the maximum height?
20
meters.
We got H to be, is it 20?
Yes, please.
Yes, please.
Okay, so 20 by 10 by another 20. So we have square root of, this is 400, 20 meters per second. Okay, now the observation is that just before the body hits the ground, its final velocity is equal to the velocity with which it moved upward. Look at the initial velocity given to us. It was 20 meters per second. And just before the body hits the ground, the the final velocity must be equal to the initial velocity. Please, are we okay?
Yes, please.
We can also use this formula, V is equal to GT. But what is this T? Look at the situation. We are looking at the velocity just before it returns, or the body returns to the ground. Okay, so the time taken to get to this point and the time taken to move from this point to this point. What's the total time? What's the total? 4. So we can also use, sorry, this will not take the time of flight. We are looking at the body falling from here to the ground. So it has to be 2. So 10 by 2 to give us 20 meters per second, just as the body, the initial velocity by the body. Please, are we okay? Are we okay? So we have used this, and we have also used this to determine the same thing. All right. Any question? Do we have any question? Nanapia.
Mr. Dear, please, why did you use the 2 seconds instead of the 4?
You see, we are looking at that the velocity. What velocity will it return to the ground? It is here. It is returning to the ground. So which velocity will you use? Sorry, which time? It is this time.
Yeah.
Okay. The 4 seconds is the total time from start to finish. But we are looking at the velocity with which it will return to the ground. So V is equal to GT, which is gravity times this time 2, so that it will be equal to 20 meters per second. And that's the reasoning. All right. Okay,
Yeah,
so
thank you.
all right. Any more question? Okay, so I think we'll end here. Please forgive me. I didn't realize that I was late. So I thought you had rather been quick for the session. I saw, oh, maybe he's in class with our seniors, but I thought you were quick on the platform, only to be told that I was about 30 minutes late, but I've made amends. Next time I'll take note, okay? Gloria.
Mr. Ida, please, with the third question, when will it return to the ground? But with that one, so they didn't tell us to calculate the total time. Or will the question tell you to calculate the total time, so just tell you to just find the time?
You see, the C question, when will it return to the ground? Yes. It's here. We are starting from here, and it's in flight. The body is in flight. So when will it return to the ground? It will return to the ground when it has covered the whole journey, isn't it?
Yes.
That's why we took this time plus this time. Because once the journey takes off, when will it return to the ground? The ground is where we started. So when will it return to the ground? So that time, this time plus this time. Are you okay?
Yes, please.
There are questions where the question actually depends on the preceding question. And I will send you those kinds of questions so you try. Okay. The question actually depends on the previous questions. Okay. And when that is given, it is usually very clear. I'll send you those examples so you look at it. Akosia.
So we are saying that what velocity will it return to the ground is different from the velocity it will return to. Right.
With what velocity will it return? You see, yeah, by the time the body returns to the ground, it would attain the same velocity as when it is moving up, just moving up.
Yes.
Are you okay? That's why we even saw that, yes, by the time it gets to the ground, the velocity will be the same as the initial velocity just when the object was thrown. Are you okay?
Zero.
Pardon?
It will be zero.
What will be zero?
Mr. The initial is U is equal to zero, but that's right.
No, the initial is, you see, the velocity with which it moved. In the question, I told you that a ball is projected vertically upward from the ground with a velocity of 20 meters per second. It was thrown from the ground with this velocity. So it's like the body is here and it's being projected. Okay, so it is going up with a velocity of 20 meters per second. By the time it returns to the ground, the final velocity must be equal to this initial velocity. And that's how come we got 20 and the initial is also 20. But what I'm saying is that if we don't use what is the velocity just before the body drops, because when the body drops to the ground, the motion has come to a stop. Final velocity is zero.
Yeah, that's what I'm saying. Thank you.
Welcome. All right, so this is where I end today's show. Okay, I'll, as usual, send you questions and upload the videos so you can have a time to review. Juviel, last question.
Sir, please, my question is, since you are trying to say that when the body falls on the ground, the final velocity becomes zero. So it means the 20 that we had is the velocity just before it falls on the ground.
Exactly. Yes, because when it drops to the ground, the motion has come to a stop, right? Okay. Then, bye-bye. You get the videos and your questions. See you next week. Please take care and revise, okay?
Bye.
All right.